Yeah, that, yes. Okay, let me start by thanking the organizers for inviting me. Once more, it's always a pleasure to be here and to see now that there is some results. You know, there are things that George has dreamt about, and now they are being realized. You know, we are hoping that in very near future we are going to have some offices to work and so on. Anyway, I'm going to talk about some aspects of flavor within the context of vector-like works. Okay, this is just, and I will be recalling, the plan of the talk is that I will be recalling some the dogma of massless neutrinos. You may ask, I'm talking about vector-like works, why am I talking about neutrinos? The reason is because I will argue that vector-like quarks are sort of cousins of right-handed neutrino, have a lot in common. And right-handed neutrinos, I mean, of course, you may say, why you believe in? I believe in seesaw because it's the simplest solution to the neutrino problem. So I believe in simplicity. Okay. Of course, there is no proof that these things are like that. How now? And then I will be talking about how vector-like works violate some of the dogmas of the SCM in a reasonable way. We know that our field was always built out of dogmas that are surpassed. The most incredible thing is parity. You know, parity was a good symmetry of electromagnetism. So the best people in our field believed in parity because they understood what it meant, and they believed that it could not be broken. You know, and it's correct to do that because if you understand parity and you see electromagnetism obeying, then you see strong interactions obeying. So it's normal that a guy like one of the best, the very best, like Pauli, he believed that parity cannot, only a silly guy could violate parity. And then the two young guys at the moment, T.D. Lee and CNN, asked a very simple question. Is there any experimental evidence that weak interactions violate parity? And they look at the literature and said that no, there is no. So they propose a very simple thing, which is let us test in weak interaction whether parity is violated. So it's important to believe that simple questions in presence of prejudices can lead to great discoveries. Okay? I'm sorry? I agree. But they, wait, no. But the experimental result came afterwards. Okay. And anyway, I was just give you just as an example. Okay, a side remark we can discuss later on. Anyway, so the standard model is 50 years old. You know, I mean, you may ask, why am I talking about 50 years? 71. You know, because I believe that it started indeed more or less in 1961 with famous paper by Glashow, who was a student of Schwinger. So we have to give credit to Schwinger to give this smart guy a nice problem. And then it ended, in my opinion, in 1971. So it took 10 years to give birth, you know. Now you may ask, why 71? To answer that question, I would ask a very simple question, which is the following. What were particle physicists doing in 1968? You know, the best way of knowing that, without inventing, is going to the proceedings of ISHEP. You know, I'm very bad at going at searching things in the net, but CERN is a wonderful institution that sometimes gives for free the old proceedings. It's a thick book. So I got it in the corridor of CERN, you know, this for our library, okay? And it's incredible. I was looking, it's certainly one of the most, I'm sorry. Some of, I'm sorry, I don't know why. Yeah, some of the most incredible conferences of all times, you know, the number of Nobel Prizes, already Nobel, or that will get that got later on a Nobel Prize is 19. You know, we don't have conferences of that type these days, you know. And nobody in 1968, remember, the paper of Glashow was already there, the paper of Salam and the Weinberg were already there. Nobody was working in gauge theories. In this respect, we have to give credit to Tini Veltman. That's a good student to look at the normalizability of gauge theory. It's not the only one, of course, other people have tried, didn't succeed, but nobody was working on gauge theories in 1968. It's an incredible thing. So in spite of recent further anomalies that have been described in a beautiful way in previous talks by Monica, and the development ruled out the standard model, you know, the development that ruled out standard model was discovered neutrino oscillations, indicating at least two neutrinos have non-zero mass. What is the key message, in my opinion, of course, everything that I'm saying is in my opinion, I don't have a proof, you know. What is the key message that nature is telling us so far? Choose simplicity. What do I mean? I mean the following. The SM is almost the simplest possibility to put together charge current interactions and electromagnetism, okay? But, you know, if it's, why do I say that the standard model is almost the simplest possibility? Let us recall lepton quark symmetry. And if you wrote in the blackboard ever the fermions of the standard model, you immediately see that the lepton quark symmetry is violated. Nu R does not appear. There is no profound reason for nu R not to be there. So what I will argue is that, I'm sorry, the neutrino nu SM is simpler. What is the nu SM? Is the standard model plus nu R. Then the following, if you follow the rules are, as you remember, is write the most general Lagrangian that is consistent with normalizability and gauge invariance. That has to include, that in itself has to include nu R. Then the following the rules, one has to include the term M nu R T C nu R, which is right-handed Majorana mass to the nu R. And immediately, with nothing else, you have the seesaw already there. Okay? So the standard model is very, if you follow the rules, you don't have prejudice, don't eliminate nu R, then you have the seesaw mechanism already there, okay? So I was a student in City College. Many people don't know what City College is, so let me say in 1 minute what is City College. City College is continuation of Bronx School of Science. I'm sure that everyone knows that Bronx School of Science, where guys like Glashow and Weinberg studied, okay? And the continuation of Bronx School of Science is City College, okay? I will come to the question later on. So Marshak, who became president of City College and used to meet with students at 8 o'clock in the morning, students and professors, you know, like Mohapatra and Sakita, Kikawa, people that later on did superstrings. We used to meet with Marshak, and he used to ask us the following question: why they means Glashow and Weinberg, put nu R in their pocket, you know? That was the question that he used to ask him. Historically, of course, the thinking of CISO was not like that. Historically, is that there were other motivations, SO10 because you could not eliminate left-right symmetry also. But what is, I found it very amazing, the special people in our field. Peter Minkowski actually was with completely different motivations. He wrote the CISO formula. So he's one of the authors of the discoverers of CISO mechanism. Okay. Of course, I mean, let me make it clear. Of course, at this moment, we do not know whether neutrinos are Dirac or Majorana particles. But if we follow this simplicity principle, then neutrinos should be Majorana particles. Okay. It's simple to choose Majorana particles. So if we continue on this line, then I know you see why people, the builders of the Standard Model, really believe that neutrinos are massless, because they knew that they cannot acquire even Majorana left-handed masses. It would not be there to all orders in perturbation theories, even if you consider non-perturbative effects, because of B minus L. So the only reasonable gut, at the time, because you wanted massless neutrinos, was SU5. And it was a strong prejudice against anything but SU5. And SU5 has the same characteristics of the Standard Model. B minus L is an accidental symmetry, and so it protects neutrinos from acquired mass. It was almost forbidden to talk about SO10. I remember attending a talk by Gelman. People very young don't remember the importance of Gelman. He was very influential at the time, and he was giving a talk at Columbia saying, "Oh, I'm so happy that I'm here. I'm not at CERN, where it is forbidden to talk about SO10." Indeed, there was a strong prejudice against anything but SU5 in CERN. Okay, that was, of course, he could not care. I mean, Gelman was a very strong personality, so he didn't care much about what people think. Anyway, I heard the story. I don't know. I never asked Howard Georgia, but that Georgia discovered SO10 before SU5, and then Glass told him, better put massless neutrinos. Then he discovered SU5. Okay, this is just a remark. There is another dogma, so you can say that massless neutrinos is a dogma that appeared at the time, and we know today we're going to violate. We know that these dogmas can be violated in a very reasonable way. There should be no flavor change in neutral currents, okay, at 3 levels, either in the lepton or quark sectors. This is a dogma, and we should be very respectful to the dogmas, because they played a role in eliminating a huge variety of models that were constructed when the Standard Model was being constructed. Many other models appear, so one has to have some discipline, and I understand why the dogmas appear. So and the dogmas are understandable. So if you violate the dogma, like the vector-like quarks, which are the subject of my talk, violate this dogma. But they violate in a reasonable way. What do I mean by that? By creating a mechanism for saying that FC and C are there, but are naturally suppressed. A phenomenon very similar to seesaw for neutrinos. Neutrinos say that the masses, the seesaw mechanism, say that the neutrino can have a mass, but it's naturally small. Here, flavor change neutral currents may be there, but they are naturally small. That was the important thing. Another dogma that I will not be talking about that here, but João Alves, and we'll talk in the afternoon maybe, and Francisco Botella also talked about it, is the no scalar mediated flavor change in neutral currents. In other words, what is the dogma for the vector currents are also applied to the scalar currents. This can be violated, okay, also in a reasonable way. The first person to conjecture, that this could happen is Weinberg, the one who invented the dogma. He said, okay, maybe in the scalar sector, maybe you could have flavor change in neutral currents, but naturally that if they are proportional to small CKM angles. Let me give you the most important example. K0, K0 bar mixing, we all know that that has to be very small. So any theory that predicts too large K0, K0 bar mixing is nonsense, okay? Now, in the models that violate in a reasonable way flavor, these are the so-called VGL models, the couplings of the most dangerous process are proportional to VTD, VTS. Now, if you remember, VTD is over the lambda cube, VTS lambda square. So in each vertex, you have a lambda 5 suppression. In two vertices, which is the triangle tree diagram, you have a natural automatic suppression lambda to the 10. So there is no problem if you have a Higgs mediating that with this kind of suppression that happens automatically in the model, you have no problem. Okay, so these are the models. I can tell you that we try to, you see, because this Weinberg has already conjectured that there could be this suppression. So we try to show that it is impossible to have, okay? In other words, to prove that there is no theory where you could have the suppression of flavor change neutral character proportional to VCKM and naturally suppressed. We tried to prove. By not being able to prove it was impossible, we proved that it was possible, and we gave an example. So that's how we invented VGL, you know, this kind of theories that violate flavor but in a controlled way, okay? Anyway, so the important point is that these dogma can be violated in a reasonable way, and I will not be talking about this here, okay? So let me go back to vector-like works. But again, show that the neutrinos violate this dogma, you know, because there are flavor changing neutrino interactions, you know, like that. Of course, it's difficult to see experimentally, but these exist. These are mass eigenstates, okay? These exist in the context of seesaw. It's very suppressed, but they exist. Now, what happens now with vector-like works? So vector-like works are very similar to nu-R. If you consider an extension of SM, which I was considering new quarks of charges Q minus 1/3 of Q 2/3 just for simplicity, if they are introduced, immediately you have, similar to what happens with the rectangular neutrinos, SU2 corresponding invariant terms like this. They are not protected by the gauge symmetry, therefore they can be naturally large. And the simplest possibility, of course, is to assume that VLQs are isosinglets. You know, I always choose the simplest possibilities. If you do that, then immediately a new scale is introduced. So this scale can be above the electroweak symmetry scale, similar to what happens with nu-R. Okay, so again, in the seesaw, 3x3 unitarity of PMNS is violated. This is an important thing. That's why this neutral current appears. So in the vector-like works, the same thing happens. You know, they are violated, but violations are naturally small. Therefore, we should not be afraid of violating the dogmas if you have a mechanism to make it natural. Now, a crucial question, of course, is what can VLQs do for you? You know, apart from being natural and so on. They provide a simple alternative solution to the Strong-CP problem without accents. There are many possibilities that were considered. The simplest one, in my opinion, is one of Barr and Nelson, you know, Nelson-Barr mechanism for having models with solution of the Strong-CP problem. They provide the simplest extension of the SM with spontaneous CP violation. I will come to this question. It's a very simple to construct a model with spontaneous CP violation, but where CKM is non-real. We heard this morning the talk about by Hanu about CKM, and we know that CKM has to be complex. Why? Because of gamma. No, not the other thing. Not what the symmetries in Fleck and in Bell and Babar. That is not enough, you know, because they are measuring beta, and beta it can be there even if CKM is real, okay? But gamma, it will be very difficult. I will not say impossible, but there is no model, reasonable model where CKM is real and gamma is complex, is not zero, okay? So gamma is a very important angle. So any model of CP evaluation has to be able to create a complex CKM. That's not easy, okay? It's possible, but it's not easy. So by that, I'm just reminding people that what does it mean spontaneous CP evaluations have a Lagrangian that conserves CP, but CP inverse should be broken by the vacuum, okay? And we know that the vacuum phase should be able to generate CKM phase, because we know that CKM has to be complex, and that we know from gamma, okay? The vector course also provides a simple framework where there are new physics contributions to BDB, there are mixing, EBS, PSP mixing. See, although fantastic experiments that are being done, still I have to check with Arne, but I think that even today we may have 10% contribution to the mixings, you know, from new physics. That is not excluded, you know, I think. Well, 10% is a big number, okay? So it's nice to see that these new physics can be tested, you know, by having new contribution PDB by mixing, D0 mixing, as well as contributions to flavor violating in the up sector. T going to C Z mu. This is a very important decay. Okay, they appear in a class of models of vector-like works. Also, now I'm going to tell you about something that is not so well known. Okay, which is they may provide vector-like works. I say may because I don't believe that has to be that way. Okay, they may provide a solution to what I call flavor alignment problem. See, this is one example of a fiction that we believe, most people believe that it is natural in the standard model to have VUS squared plus VUB squared of order lambda 4. Now, a simple calculation, and if you don't believe, you don't have to believe, I can show you in the coffee break, you know, that even in the standard model, even in the limit where only the top has mass and the bottom, that's deep, what I call deep chiral limit, even in that limit, VTB can be meaningful and actually of order 1. We know that it's close to 1, just 1. This being 0.9999, that's the result of believing unitarity. But as far as natural prediction of VTB in the standard model should be of order 1, but could be 0.7, 0.5. We don't know why nature has chosen such a small number, okay? This can be proven in a very simple way, okay? The way you do it, I will not do it here. The way you do it, you start from the most general matrix that it has two eigenvalues, 0 and 1 different from 0, the most general one. You know, and then for the ups and for the downs. And then if you do that, immediately you can show that in general mixing is meaningful and it's of order 1, not 10 to the minus 3. Okay, so this is an open problem, and I don't know. Actually, I don't know any model that does that. You know, so that's one thing for the young people that want to discover something fundamental is a natural way, but being careful because otherwise you are cheating. You know, a model where really you have to have VTB close to 1. Okay. A very good possibility is left-right symmetric model, but even in left-right symmetric models, that does not. I'm saying left-right symmetric models because they can, in some schemes, acquire having Yukawa couplings parallel to each other. So if you have that, you may have a chance. But I don't know any model, even within left-right symmetric models, that predict that VTB is very close to 1. Okay. Now, I would say the squartest will be. How much time do I have? Oh my God, I'm going too slow. Yes, but because another characteristic of ELQ that is very interesting is the fact that they may populate the desert, in other words, desert between V and the higher scale could be Gatra and Planck, without worsening the hierarchy problem, because chiral symmetry protects them. This is what an old beautiful paper by Pierre Ramon, Fermions in the Desert, a talk giving at Erice many years ago. Anyway, it emphasizes this. Vector-like works don't need to get the MGAT scale. It could be a few TeV, no problem. That in itself doesn't make the hierarchy problem worse. It does not solve it, but don't make it worse by having something in the desert. Okay. Now, also they may provide. I say may because I'm not sure that this is the only solution or the most elegant solution. A solution to this problem that I mentioned, they may provide. They may also provide an explanation to the recent discovered, it's not completely sure, VCKM unitarity problem. You see that this is something that was discovered experimentally, and there is some nice work by Belfat and Bergiani. We also did some work on this, and our student Pedro Pereira will be talking about that. Okay. Now, this is a very exceptional thing, but let me now question: should we take this seriously? See, in this collaboration, we had young people. We don't ask young people to be working on a field, on a subject that came from experiment that good theoreticians think that it's very, and experimentalists think that it's a very doubtful result. So first, before encouraging our students to go along that line, I made a phone call, to specialists in the field. That's a good technique, asking those who know more. So I'm showing here, this has to do with this meeting because it's showing how in some bars in a restaurant in Lisbon, things COVID is not obeyed at all. At that time, of course, COVID didn't appear at that time. It's an old picture. You see I'm here, Di Marciano is here, this is Guy, and then these are two, this is a mathematical physicist, this is another Luis Laboro, Jean-Marc Tirage, Leval, charlatans. But you see, this is another table. You see, this is another table. So everyone is on top of each other. You see, that's how it used to be before COVID in Lisbon. This is a restaurant called Bota Alta. Okay, you cannot even distinguish, between one table and the other one. There are three tables here. Okay. Well, I will not. I don't have time to finish my talk. But another important thing is that VLQs can provide a simple framework where you have a common origin of all CP violations. In other words, you could have CP, as you know, you have the CP violation in the quark sector, CP violation that the people at Dune and other laboratories will try to discover in neutrino oscillations. This is the phase that appears in PMNS, the Dirac phase that appears there. And then they are also very important to generate the observed baryon symmetry of the universe through leptogenesis, and you can have a spontaneous CP violation in which you have only one phase, but that phase is enough to produce all these manifestations of CP violation. I don't have time to go through the example. There is an example of where you have a simplest model with vector-like works. You start just from the standard model, and then you introduce the vector-like work of charge minus 1/3, and you write the most general Lagrangian. And then you have here, you have this zero that is obtained through a Z2 symmetry that makes it possible to the argument of MD, to be zero. So you have a simple solution to the strong CP problem. That's, as you know, aesthetically CP per aesthetically should be zero at 3 level, and you can calculate corrections. Okay, that is in this particular model. It shows all the characteristics of vector-like works. It also shows, okay, this is the organization. I don't have time to go through that, but you can show that this is the these first three lines of this 4x4 matrix is VCKM, now extended through the mixings with the introduced new quark. Then you have K dagger will be equal to 1. It's violated, but this violation automatically is small. R and S are naturally small, okay? So, and then this is a very important formula. You have here a very interesting thing that the effective matrix for in this case, for the down quarks is MD dagger, which comes from standard model plus a new contribution. This new contribution is of the same size as this one in general. You know, it's enough to have MD of the same order as capital M, okay? I remind you what is MD. You see, MD is this line here, and this is capital M. Okay? This is obtained through Yukawa couples and a large vacuum potential value of a singlet, and then M is just a bare mass. So they should be not very different orders of the same order. It's perfectly natural to that to happen, and then that is enough to have two terms contributing to the effective mass, and that can be of the same order. You see, that's how in this model the big difficulty of creating CKM from Yukawa couples that are real is possible, because you see MD comes from Yukawa couples, it's real, but then there is a new contribution that is of the same size. So this can have deep consequences for those who try to from in a bottom-up approach to guess through symmetry and so on what is the measure down type, for example, Yukawa couplings. That can be misleading because there is a presence of new contribution of the same size, okay? And you are trying to fit this, but this is not the fundamental thing that is going to dictate what K is. K is the CKM matrix, you know. I'm sorry, the PMNS matrix. Okay, so I think that conclusions, I can go to conclusions. So we need a guiding principle in the search of new physics. A possible principle is simplicity. And we have argued that the new SM is simpler than the SM and is in agreement with the experiment. Neutrinos should be majority parts, in my opinion, and VRQs are cousins of nu R and may also violate some of the dogmas of SM. Since I have to keep talking about violating dogmas of SM, I should say there is no doubt that SM made by the great masters, you know, Glashow, Weinberg, Salam, and we should include also Braut, Angler, and Higgs, you know, this is the greatest achievement of theoretical physics, you know, after quantum mechanics and relativity. There's nothing. I'm sure that superstring people will be shocked. You know, how can be something? This is by far the greatest achievement of theoretical physics, you know, and the experimental physics, okay, after relativity and quantum mechanics, in my opinion. Even if they made, in the quotes, a mild mistake with the nu R, you know, that's a minor thing, you know. Standard model is fantastic. Okay, that's all.
Yes. Of course, unification with SU5 or SU10 should not be a dogma. But I just wonder in which representation of this group one may take this quartz, which are colors, so cannot put in the singlet, and I don't see where.
Well, you know, Feza would say like very much, E6. In E6 appear vectorized quarks, in E6, for example. But there are many other schemes where vectorized quarks appear.
Singlet of the Corfu2021.
If you go at the level of low level, yes. They may not be singlets or other things, but you can have.
I see many questions. One there. Are you first? Sorry.
I want to comment on the way of suppressing flavor-changing observables that you were advocating.
Yeah.
So they are suppressed in a controlled way by small couplings, right?
No, but wait.
Scalar Yukawa couplings with flavor.
No. They are they are suppressed by essentially by the letter weak scale divided by a scale of vector-like work, which is one scale up. Can be it's enough to be 10 times.
Yeah,
less.
but what is suppressed are couplings, right?
No,
There-
no.
there are couplings.
No. You may have also couplings, but you don't suppress through these couplings. It's like seesaw.
But in your model, you have flavor changing Yukawa couplings, right?
Well, it's not very meaningful to say. What we have is the mediated neutral currents violate flavor. Yes,
Okay.
and they are naturally suppressed, entirely similar to seesaw. Remember, I even wrote explicitly the diagram nu1, nu2 coupled to the z. That exists. People forget that. That exists in the seesaw, simple seesaw. Okay, we can forget because it's very suppressed. If
a bit setting boson interactions to flavor cellular currents at 3 level for the heavy neutrinos. And there's a boson interaction. It's the observation by Pascos, I think that's the theorem. Right. So let me come to my question now. So just to you were advocating, or at least you seem to be a good believer for spontaneous CP violation, right? So, and one of the things, of course, nowadays we are. I mean, first of all, I like your overview for the young generation, even for myself, to remember all that stuff. That the data we have now from observations, chronological observations, become quite tough. We know that spontaneous CP violation, because it has to be exact, the spontaneous CP violation, so that the quality of the theta problem works, will produce domain walls. And actually, in the recent papers we wrote with Richard Buddy, I mean, here, this can be a problem to the extent that we may have slowly to abandon that dogma of spontaneous CP violation.
not a dogma. First of all, not a dogma. I don't think, but we should say whether it is possible to have spontaneous CP violation. That because the constraints from cosmology, you have to take very careful, because sometimes. Well, I mean, we don't know what is the value of cosmological constant, right? Do you have a model for that? Why is it so small?
Different problem.
Right, of course it's a different problem, but it's a very important problem, If you live well with a standard model, any other model that doesn't solve cosmological constant, I mean, we should not be so that you cannot talk about spontaneous CP violation because of that problem, in my opinion, okay? Maybe what I can give you an answer that a guy that will solve completely the cosmological constant problem will also probably solve the problem of CP, that's. But I agree it's an important thing, but we should not exclude the model just because of that. Yes. I know, but I don't know if they are not making a mistake. I will tell you, I'll give you an example. Even if you have a model that achieves, even if you have a model that achieves that both things are, both currents, masses are diagonal simultaneously, the ups and down, there is a problem that there is no reason in the standard model, there is no communication between up Yukawa compass and down Yukawa compass. They don't have anything to do one or the other. Therefore, even if they are diagonal simultaneously, there is no reason for the T happens to the B. Okay. For example, the ordering is meaningless. Okay, you may always choose DSB. Okay, by choice. But then the other way ordering is meaningful. In the standard model, it is as likely that T couples to B as T couplings to D or S. Okay, it's the same in the standard model. There is no reason. Yes.
So what is wrong with just Dirac neutrino?
No,
One right-handed, a Dirac
No,
neutrino.
no, of course,
This is
I
the
agree.
simplest.
I mentioned that there is no evidence that neutrinos are major. That is an experimental question, very thing. What I share with you is my prejudice. I prefer, I think that it is more natural to have what I call new SM. You know, new SM means the addition of right-handed neutrino.
So right-handed neutrino and Dirac mass, nothing else. This is the simplest version.
Oh, yes, you mean, but it's very unnatural to put this, you call coupling small, but I agree it's a possibility, it's a prejudice, I agree.
Small parameters, so what? Just
Okay, I would agree. If you are willing to buy that, for sure, it's one possibility. I would prefer the seesaw because it gives a justification why neutrinos are so light. Of course, electrons are also light. I agree with you. I agree. Well, look, Alexei. The problem is obviously deep and serious because otherwise, Weinberg and Salam would not have hide the Noir because they found it putting the Noir without having. They didn't know about seesaw. It's a very unnatural thing, you know. To have neutrinos for the mass. But I agree with you. That's another line of thinking, okay, which in a way is simpler, okay.
Okay, so
but people thought that neutrinos are massless. And the fact that you do not include R is just explanation that neutrinos are massless.
Yeah.
This argument is gone.
Yeah.
okay, but
Yes.
let's discuss it later because we have to continue.
Yeah.
And thank the speaker again. So the next talk will be online. It will be given by Steve King on twin Patti-Salam theory of the flavor with the TEV scale vector laptop works.
Okay, thank you. Could I share my screen? Let's see. Okay, I hope everyone can see that and hear me. So thanks to the organisers for inviting me. And unfortunately, I couldn't come this year for our University of Southampton are not permitting travel. So Pasquale, my colleague at Southampton, he's in the same position as me. So anyway, I'm very jealous of you all being there. It must be wonderful. So anyway, today I'm going to talk about a model called twin Patti-Salam theory of flavor, which contains a TeV scale vector leptoquark, which can have implications for the B physics anomalies, which you heard about earlier this morning. So it's based on this paper, which is submitted to JHEP. It's under review. Okay, so let me begin with the flavor problem. So this is what we're confronted with in the standard model, trying to understand these pattern of these particle masses represented by the heights of these towers, which I've actually scaled. Otherwise, they would all be flat compared to the top quark. So you see the true height of the neutrino mass tower is 10 to the minus 11 times the height shown, and so on. So this is the flavor problem. And in the standard model, what we're told is that all of this structure arises from these Yukawa couplings. So this is the Yukawa coupling a left-handed fermion to a right-handed fermion with these numbers Yij. So mathematically, it appears like this, and these numbers Yij are supposed to give rise to this pattern. And in the standard model offers no explanation for what these numbers are, which gives rise to this pattern. So this is what people sometimes call the flavor problem. And you may question that the standard model is the final word on this, because it seems a bit of a puzzle. How do you get all of this structure from these numbers, which seem arbitrary? But that's not the only flavor problem. These days, we have other flavor problems related to lepton flavor universality, which we have some hints about, as you heard in the first talk this morning. So let me turn to that. So, well, it made the BBC News this year in March, this RK quantity, and I can be really quick here because Monica has described this very well. It's basically a violation of the universality between muons and electrons. So it's the ratio of B decays into muons divided by B decays into electrons. And in the standard model, this ratio is approximately equal to 1. And the reason is because of this diagram above, which is one of the diagrams that contributes to B to this particular transition, B to K, lepton, anti-lepton. And you can see in the standard model, it goes through this so-called penguin diagram. I think there's also a box diagram, but this is one of the diagrams. And you can see a photon or a Z. And in the standard model couples equally, the photon and Z couple equally to muons and electrons. So in the standard model, you would expect this the ratio of these two decays to be equal to 1. Well, of course, actually, as Monica described, experimentally, you can use the double ratio using the Jabe psi. So you've all heard Monica's talk, so I'm not going to repeat that. But so it's the double ratio actually that's measured. So this also you heard in Monica's talk. This is RK. History of RK, going from Babar, Bell, LHCb at 5 inverse femtobarns, and the recent data at 9 inverse femtobarns. And you can see that it's significantly different from 1. And the number is 0.846, the ratio. Remember, it should be 1 in the standard model. And these are the errors, statistical and systematic. So this amounts to a 3.1 departure from lepton flavor universality. So still not 5 sigma, but consistent over time, it seems, with the 5 inverse femtobarns and the 9 inverse femtobarns. In fact, the central value, I think, is identical, just coincidentally. But anyway, it seems to be holding up, and it'll be interesting to see if it holds up in the future with the CMS measurement and, of course, Bell and future LHCb measurements. So that's the status. Now, to explain this, you need to add something to the standard model. And what people like to do is add these operators called O9 and O10. Now, O9 is basically a coupling which mediates the transition. It involves strange bottom and muons. And O10 is a similar operator, except that it, instead of having a vector coupling to muons, a gamma mu, it has a gamma 5, so it's an axial vector. And if you look at the fit, this is a recent, there are many recent fits. I'm sorry for if this is not your favorite one, but there are several of these on the market. This is just one of them that I picked up, which fits this new physics, delta C9 and delta C10, which are the coefficients of O9 and O10. And you can see that the best fit is different from 0. Remember, these are the new physics contributions. So you'd expect this star to be 0 if it agrees with the standard model. So it's significantly away from 0. And it's actually consistent with delta C9 is minus delta C10, which is this diagonal line here, goes through this orange band here. This is the 1 sigma global fit. Now this fit actually includes not just RK, but also angular observables, and indeed BS to mu mu, which is going horizontally there. So this orange fit includes all that data. This means left-handed, of course. If C9 is minus C10, this means left-handed. It's vector minus axial, B minus A, which is another way of saying that you have left-handed muons. Both operators involve left-handed quarks. And the fit requires that this coefficient should be about 1 divided by 35 TeV squared. So that's the global best fit value. And that's a mass scale, a new mass scale, which sets the mass scale of the particle which is being exchanged, which is giving this operator. So for example, it could be a Z primed, which the operator would come from a diagram like this if it was a Z primed, or it could be a leptoquark, which I think Ivo mentioned in his talk, the leptoquark exchange possibility. So these are two possibilities that are used to generate the operator. Of course, this doesn't mean that the mass of the Z prime and leptoquark has to be 35 TeV, because you get other coefficients coming in into these couplings. So it depends on the model, actually, what the mass of these things are. But typically, they can be of order 1 TeV with some small couplings. Okay. Monica also mentioned bottom to charm tau neutrino measurements, which are described by these ratios RD and RD star, which are the ratio of B to D tau nu over B to D lepton. This lepton is the sum of the electron and muon contributions. And you can measure this for D and D star, and you can plot the results in the plane of RD star, like Monica did. And you can see the history of these measurements here from Babar. Bell is here. Bell 19, the latest one, I think. And the best fit to all of them is this red. This is the flavor averaging group global fit to all of these data. And you can see that it differs from the standard model. Here's the standard model, this little cross here. This didn't make the BBC news, but nevertheless, it's still a 3.1 sigma lepton flavor universality departure from the standard model. You see this little almost invisible ellipse here. This is the 3 sigma ellipse, so this is just outside that. And so it's about 3.1 sigma. Coincidentally, it's the same number of sigmas as the RK deviation. And in the standard model, it comes about through this tree level diagram here with a W exchange. So apparently there's some hint for new physics which is competitive with the W exchange in the standard model. And these are the possible operators that are responsible, could be responsible for the deviation. You can have vector, tensor operators, scalar, right-handed scalar, left-handed scalar. These are the projection operators, PR and PL, left and right, right and left. So the Hamiltonian then involves the standard model coupling, which is proportional to the Fermi constant and VCB. But then you can get these new physics contributions coming in here. And for example, well, here's the W, standard model W. That's the one there. But you can also have a W primed that could be responsible. And you can have charged Higgs exchange, which could give these scalar operators. And then you can have leptoquarks. And leptoquarks actually can contribute to all these operators, all of the above. Each one contributes to slightly different combinations. But the leptoquarks can be either scalar leptoquarks, spin 0, or vector, spin 1. And they can have these quantum numbers under the standard model. So this is under SU3, SU2, U1. And one of them is special. That's this U1 here, this vector leptoquark U1, which apparently can explain both RK and RD. So you can do everything with one new particle. So that's a good motivation to have a look at that particle. So here it is. Here's the Lagrangian for that new leptoquark, which I'm going to call U1. It's just, some people call it U. Here's the Lagrangian. You've just got to connect it to, and this is like F mu nu in standard model. This is the mass of it, mu squared. This is the coupling to some current, and the current is the simplest model is where you couple it to doublets, quark doublets and lepton doublets here with a coupling constant Bi alpha. And first thing to ask is, when you write down this Lagrangian, is it consistent with LHC searches? And that's the purpose of this figure here, is to show in the plane of the coupling GU and the mass mu, you can see that it would be excluded for masses below a TeV. This is this CMS search here. But above a TeV, it's not excluded. So the future, for example, in future searches that will have 300 inverse femtobarns can push it out to 1.1, 1.2, 1.3 TeV. So it could be, if it's around just above a TeV, it could be discovered at run 2, which is interesting. Okay, run 3. So here's the another mechanism for producing it. This is proton-proton goes to tau plus tau minus. This is a T-channel exchange. So these bounds, these vertical bounds, are coming from S-channel exchange for pair production of the vector leptoquark. These lines here are coming from T-channel exchange, and the present limit is this one here. Okay, so that gives the limit on the coupling as a function of the mass. And then in the future, at 300 inverse femtobarns, it should go down to here. So you should start to squeeze it. Okay, and these green bands are best fit values for explaining the anomalies, which I'll come on to in a moment. So these are the numbers to have in mind. It has to be bigger than 1 TeV, and the coupling has to be smaller than 2.5. I said 2.5. It looks like actually 2.3 from this figure. But anyway, these are the rough present bounds. Question? Okay, yeah, please feel free. Yeah, I should have said, please feel free to interrupt me and ask questions at any time.
It's just saying that you have 10 minutes.
Oh, okay, thank you. Right, so these are the fits to RD and RK. Okay. So this is the diagram that gives the RD decay. It's beta tau C, and this is the RK fit. And you can get fits in the parameter plane of beta C tau, nu tau, which these beta coefficients are here, and this depends on the mass and the coupling across here. So the best fit region is here, and for RK, you're in these sort of hyperbole here, coming from this diagram here. So this diagram depends on beta B mu, which is this parameter here, and beta mu s, which is this parameter here. This axis is scaled by VCB. So there we are. It just shows that you can fit both of them. You have enough parameters to fit both. Now, because I have 10 minutes or so, oops, I'm going to get on to theory now. So this is having sort of argued that this vector lepton quark is interesting. Now the question is, where does it come from in a theory? And one place it could come from is Patti Salam. So just remind you about Patti Salam. Patti Salam is based on SU4 color, plus SU2 left, plus SU2 right. And the left-handed ones, quarks and leptons, transform in these kind of multiplets here, and the right-handed ones here under SU2 right. And the idea is that the leptons are the fourth color, you see? So you're extending SU3 color to SU4 color to embrace the leptons. And having extended the gauge group, you can have a gauge boson called, this is the U1 gauge boson, in fact, that makes a transition from quarks to leptons. And this is exactly what you want to explain these anomalies. And the U1 is fitting nicely into the SU4 of Patti Salam. And it can explain both RK and RD for a 1 TeV mass, or just above 1 TeV, as we just saw. But unfortunately, a TeV mass in Patti Salam is not allowed. This SU4 breaking, which generates the mass of U1, you have to do that at a higher scale because of this process here, K long to mu e, which is basically mediated by a T-channel exchange of this U1 gauge boson, which is unsuppressed by flavor because you have second generation strange to second generation muon, first generation down to first generation E. So you get zero suppression really from mixing. And the limit on this is about 1 PeV, which is 1,000 TeV. So that seems to be at odds with the desire to have this thing to be at 1 TeV. So the conclusion is it's difficult to reconcile in a complete UV complete Patti Salam model. Well, it hasn't stopped theorists speculating on possible UV completions. So here's an incomplete list given in a talk by Andreas Krivelin. So you can see that there's a SU4 plus SU3 plus SU2 plus U1 model with vector-like fermions. That's been proposed. And then various other models. I don't have time to go through them all, but these are some of the references. But the thing is, none of these, this is the point I want to emphasize, none of these models attempt to explain the origin of quark and lepton masses, which to my mind should be linked to any flavor anomaly, should be related to the physics of quark and lepton masses. So that motivates this model, this twin Patti Salam model, which I'm going to talk about in the remaining 10 minutes or so. So each circle, I should explain this picture here. I'm using a pictorial notation where circles represent gauge groups. So this twin Patti Salam is based on 2 copies of Patti Salam group. You've got the red Patti Salam group and the blue Patti Salam group. And the idea is that at high energies, by high I mean bigger than 1 PeV, the second Patti Salam group gets broken, but the first Patti Salam group only partly gets broken, and in such a way that this SU4 from the first Patti Salam group survives. And the idea is that this U1 vector leptoquark is living in this first Patti Salam group here. And so that Patti Salam group gets broken at a low scale, 1 TeV, and gives a 1 TeV mass to the U1. And that gives rise to the standard model. So that's the idea of the twin Patti Salam. And this is an attempt to explain the origin of fermion masses as well as RD and RK. So that's its main feature, is that it does everything, or attempts to do everything. Due to time limitations, I'm actually going to ignore the first family and neutrino masses, which is sad because I spend a lot of time working on those. But I just simply don't have time to do it and to do them in the talk. So please let me invite you to take a look at the paper for the full full model. So in this talk, only second family and no neutrinos. So sorry about that. So here it is. Here's the model. We have 3 chiral families under the second group. That's the blue group. And here they are, 3 families which transform, 3 chiral families which transform under the second group. And they do not couple to U1. Remember, this vector leptoquark is living in the first Patisalam group. So they don't know about the U1 vector leptoquark. But then we also add a 4th vector-like family. And fortunately, Gustavo has done a nice job of introducing vector-like quarks and leptons. So I don't need to say much about those. The motivation for those is clear. And but the idea is that this 4th family, this vector-like family, transforms under the first group, the red group. So you see you have this structure here with the red group. So the vector-like families do couple to the vector leptoquark. And then we add some Higgses, and these Higgses we allow to transform under both groups. So these green Higgses here, they transform under both first and the second Patisalam group. And we have 2 sorts of Higgses, these Phis and these H's. But crucially, there is no Higgs H122 under the second Patisalam group. So that does not allow Yukawa couplings. So these kinds of Yukawa couplings to the chiral quarks and leptons under the blue group are simply not allowed. So the question is, where do the quark and lepton masses come from in this model? And they're generated, the answer is they're generated by mixing with the vector-like family. So we have these 2 kinds of diagrams, both involving phi and h. Well, one's involving phi and h, one's involving h bar and phi bar. One involves this vector-like mass, this 4th vector-like mass involving the doublets, and this is the 4th vector-like mass involving the singlets. I'm using the charge conjugate notation. So whenever you see a C, you can think of it as a right-handed fermion. And to cut a long story short, these diagrams give rise to these Yukawa matrices. You can see from above, this is the 3rd family. The 3rd family Yukawas are generated from this diagram. And the 2-3 block is generated from this diagram. And I'm working in a particular basis here, a convenient basis. So I'm rotating, without loss of generality, I'm rotating to a basis where this diagram contributes only to this 3-3 element. And I'm going to choose this ratio, this 5ev vacuum expectation value over this M4 side to be of order 1, and this to be very much less than 1. So this will generate a hierarchy. So the hierarchy of masses between the 3rd and the 2nd family comes from the hierarchy of masses of the 4th vector-like doublets and the 4th vector-like singlets. Incidentally, Gustavo only had the right-handed ones here. He didn't have the doublets. So I'm going to need both, as in our complete family. And if we break down the group under 4321, remember my original diagram of the symmetry breaking, these Higgses break down into actually.
You've run out of time.
Okay, I think I have. Okay, I've run out of time. Okay, should I just stop then?
Finish quickly, please.
Okay, I think I only have a couple more slides.
Okay.
So if that's okay, or I can just stop.
It's okay.
Okay, so I'll be brief. So when you break it down, you see that these diagrams gives rise to the up quark matrix here, the down quark matrix, and the charge lepton matrix. And you can see that you have a different Higgs, different personal Higgs for each mass. So this Higgs gives rise to the top quark, this gives rise to the charm, this gives rise to the bottom, this gives rise to the strange, tau, and muon. So you've got a separate Higgs for each of these. Remember, in this talk, I'm only doing 2nd and 3rd family for simplicity. And briefly then some phenomenology. In this model, we have the vector leptoquark, which couples only to 4th family, no chiral couplings. Also contained in the SU4, you have this coloron and this Z primed. But these have suppressed couplings to chiral quarks and leptons given by these ratios couplings. So if we take this typical benchmark, you can see that the G4 is bigger than the G3 and the G1. So these are very small ratios. And also in this benchmark, we have TeV masses for the Z-primed vector leptoquark and Colleron mass. And then finally, this is my penultimate slide, actually, my last real slide. I said that there was no couplings to chiral quarks and leptons, but actually these Higgses generate mixing between the fourth family and the predominantly the third family, and this mixing generates couplings of the vector leptoquark to chiral quarks and leptons. And dominantly, you only get the third family coupling through this diagram here, so you only get this QL3 lepton L3. But after diagonalizing the mass matrices that I showed you on the previous slide, if you go to the mass basis, then you do generate these beta couplings. And here they are. So for RD, you find a beta BL approximately 1, beta C nu tau L is the ratio of MC over M top. That's because of the Yukawa mass matrices I showed you before. So notice that I'm predicting what these betas are now because we have a theory of quark and lepton masses. And for the RK, you get this diagram. So on the left, you get this beta B mu, which is M mu over M tau. And on the right, you get beta S mu, which is this M mu over M tau times MS over MB. Now, unfortunately, this ratio of M charm over M top is about 0.007, which turns out to be too small compared to the best fit value. The best fit value is about 4 times VCB, which is about 0.16. So there seems to be a mismatch here. And probably you could do it with fine tuning, but if you don't want to tune because you have lots of Yukawa couplings in this model, but if you refuse to tune the Yukawas, you have to conclude that it's a bit too small. So there we are, I'm finished. So here's the conclusions then. Fermion mass and mixing is a great mystery of the standard model, and which should or may or should be related to recent B physics anomalies, I think. The RK and RD anomalies may be simultaneously explained by a TeV scale vector leptoquark from Pati-Salam. But the Pati-Salam typically is broken above a PeV to avoid these flavor changing problems, K long to mu E. So this requires some non-trivial UV completion. And what I've shown in this talk, I've talked about this particular twin Pati-Salam model, which yields a TeV scale vector leptoquark and explains fermion masses, which are usually not addressed. But unfortunately, it seems to be a victim of its success because it's having predicted the mass matrices, you can then predict these couplings. I'm no longer free to play with them. And we've seen that they do not yield large enough couplings to explain RD given the current value. So if you like the model, then you would have to hope that the value of RD would have to come down a little bit. Okay, that's it. Thank you for your attention. And yeah, sorry for going over time a little bit.
Are there any questions? Oh. So there is one here.
Hi, Steve. Ivo here. It's a pity not here. It would be great to have you at the excursion tomorrow. A question about your talk. So I remember we worked together on something a little bit similar to that, where we were introducing the leptoquark more or less by hand, but we were just doing precisely RK. So is it correct that this is kind of a UV completion of that, but you get, because of you put the twin Pati-Salam, the extra effect of the RD, but unfortunately then you predict it, but it's not enough. Is that a correct understanding?
There are some similarities, that's for sure. Let's have a look. Let's have a look here. So you can see that the similarity is that we're just like in our model, Ivo, we're generating the fermion masses and mixings through these kinds of diagrams here, which is what we did in our model. The difference is that in our model we had a scalar leptoquark, so we had diagrams similar to this, but with one of these Higgses replaced by a scalar leptoquark. Whereas in this model, I'm actually using the gauge structure of the Patti Salam to do it. So I'm using the SU4. I'm using the SU4 gauge boson here. So I'm not actually adding a scalar leptoquark like we did. So it's coming through the gauge principle rather than the adding an extra scalar with Yukawa couplings. But the idea of generating the origin of Yukawa couplings idea is definitely related to that philosophy of generating masses through diagrams like this. Yeah, that's right.
Thank you, Steve.
Okay. And I'm very jealous that I'm not going to be on the excursion, and indeed at the conference.
Hello, Steve. This is Paul Frampton,
Hi, Paul.
and you will be sorely missed on the boat ride tomorrow.
I'm sure it'll be wonderful.
But listening to your talk, I had a flashback for some reason to a paper I wrote with Shelley in the 80s, shortly after SU5 was apparently killed by proton decay. All I remembered about the title, the paper had a great title. It was called Staying Alive with SU5.
I remember the title.
That's the only thing that's worth remembering, except that's because Shelley had seen some movie with John Travolta the previous day or something. Anyway, it had a great title. But inside the paper, we had the bright idea of adding vector-like quarks in between the weak scale and the gut scale, just to fix up the proton lifetime, which we could do almost arbitrarily. I was wondering, and you have a lot of vector-like quarks, so I wondered if you'd sort of entertain the idea of changing the proton lifetime.
Right. Okay. So that's interesting. That's my first comment. Yes, we do have this family of vector-like quarks. I haven't considered unification in this model yet. So this is really is two copies of the Patti Salam group. I haven't actually considered unifying these into SO10s or two SO10s. It could be, probably it's going to have to be two SO10s.
Do you proton decay at all?
Proton decay is absent. Yeah, in standard Patti Salam, you don't get proton decay, as you know, and this is no different. Yeah, this is no different. So we don't get proton decay in this model. But if it was extended into a unified model in terms of SO10 squared, then yeah, you would bring in the proton decay at that stage. Yeah.
Thank you very much.
But yeah, I haven't.
I think there are no more questions, and let's thank the speaker again.
Okay, thank you.
Bye-bye.
Thank you, thanks.
So now we move to the next talk. Are we ready? Yes. Okay, so hello, Antonio. Next, given by Antonio Di Domenico on recent results with entangled neutral kaons at Chloe 2. Please start.
Yes, sorry, okay. Okay, can you hear me and can you see?
Yes.
Okay, so first of all, let me thank the organizers for inviting me, and I'm sorry not to stay physically there with you, but was not possible. Okay, I am going to summarize the status and some recent results obtained in the analysis of the CLOE and CLOE2 data about neutral kaons, actually entangled neutral kaons. I'll show you in a moment. Okay, so as you know, the CLOE experiment okay, was collecting data at the plus collider in Frascati, Daphne, that was a collider running at the Phi Meson peak, so actually a Phi factory, producing in the first data taking campaign I mean, the experiment was collecting 2.5 inverse femtobarn integrated luminosity, corresponding to something like 2.5 billion K-short long pairs. The detector, you see here a sketch of the detector, is composed mainly by two sub-detectors, a large volume drift chamber allowing I mean, the decay of decay long inside this volume, a large fraction of it, and surrounded by an electromagnetic calorimeter with very high performance, especially about the timing performance, and both immersed in the magnetic field provided by superconducting coil, about half Tesla. So after the first data taking campaign that took place in the years, let's say 2000, 2005, 2006, then the detector has been upgraded with several sub-detectors to improve, I mean, the performance, and especially with an inner tracker close to the interaction point to improve vertex resolution close to the interaction point. And after also, I mean, an upgrade of the Daphne machine with a new scheme based on the crab waste design, the second data taking campaign of the experiment, named at this point CLOE2, started at the end of 2014 and was completed in March 2018. You see here, okay, in blue, the instant luminosity for the first data taking campaign and the improvement that has been provided by Daphne in the second data taking campaign. Overall, both CLOE and CLOE2, I mean, the two data taking campaign correspond to almost 8 inverse femtobarn integrated luminosity, corresponding to 8 billion K-short long pairs, and obviously also 310 to the 8 ETAs and so on, and then is essentially the largest sample ever collected in plus and minus collisions at this energy. So concerning the neutral counts that are produced in the decay of the Phi, as you know, they are produced with the same quantum numbers of the Phi in a totally antisymmetric entangled state that is antisymmetric in any basis, and provided that the decay length of the K-short and K-long are very different. So these has quite a unique features, as we'll see in a moment. But however, this particular combination of the entangled state and the difference of lifetimes allows to tag, I mean, to prepare, let's say, a pure K-short beam with I mean, the highest purity, depending on how much, I mean, the decay that you choose and how much the difference of time between the two decays, how much long is this distance, okay, allows the preparation of a K-short, pure K-short beam. You have in this left plot here on the left, yes, you have a sketch of how it works in practice in CLOE. You detect actually not even a decay, but an interaction of decay long in the calorimeter. Here, the diameter is 4 meters, so the radius is about 2 meters. So after 2 meters of traveling of decay long, so these identify, I mean, decay long, and this tags a decay close to the interaction point due to decay short. Okay. This is the way in which obviously the opposite for K long. So I'm going to present some recent results about the studies of K short that is possible in CLOE. So first, let me briefly describe the first measurement of the branch ratio K short in pi mu nu, the symplectonic decay with the muon, that was never measured before and allows an independent determination of the CKM matrix element VUS and the test of lepton flavor universality when you compare with the K short in pi nu. So the analysis essentially, okay, is based on the 1.7 inverse femtobarn. The tagging, as I told you, is based on the mechanism I just sketched a moment, a couple of slides ago. And the analysis, okay, the selection is based on, I mean, a BDT analysis based on kinematic variables, and then a cut-based analysis on time of flight variable. You can see that okay, the plots, I mean, the difference of times that the different times reconstructed in the calorimeter of the two tracks from the K short, and here you see the signal, okay, with that is with an overwhelming background that, however, after cutting on this variable, one is able to reject. The efficiencies have been not only based on Monte Carlo, but on a control sample of early decays of decay long that mimic decay short decays. So finally, this is the final variable that has been used for the measurement of the branch ratio. You see the mass mu squared, and you clearly see the peak of the signal with 7,000 events. And finally, this is the result of the branch ratio K short. We used as a normalization the K short in pi plus pi minus. So it's 4.5 10 to the minus 4, the dominated at this point by the systematic uncertainty. With this result, we are able, this result is in agreement with what you expect from lepton flavor universality, the evaluation of the branch ratio, assuming lepton flavor universality. Actually, you can test the lepton flavor universality. You see here the result should be 1, is consistent up to a few percent. So concerning other decays of decay short, we are searching rare decays signaling CP violation of decay short that was never observed before. So we are looking to the K short in 3.0 and also K short in pi plus pi minus pi 0, that however is not a pure violating CP violating decay, but only on some angular momentum components. I'm not going to describe this analysis that is still in progress, but just I would like to sketch the status of this analysis, K short in 3.0, that actually we already performed on a subsample of the CLOE data, and we published the result, putting an upper limit on the branch ratio K short in 3.0 up to 2.6 10 to the minus 8. And that, okay, standard model predicts at the level 2 10 to the minus 9. Actually, we are analyzing additional 5 inverse femtobarn collected include 2, and then we will combine all together the results. Okay, the analysis, I mean, the search for this decay is clearly, I mean, you are looking for the 6 photons coming from the 3 by zeros, and as I told you, the tag of decay short with the AK long crash on the calorimeter. So overall, you are looking for 7 clusters, and you use as a normalization the K-short 2 by 0 sample that is very, I mean, is a huge, obviously, is allowed decay of the K-short. And okay, we are progressing with this analysis, studying okay, the several variables, and we are actually performing a blind analysis and studying with the Monte Carlo the contributions and comparing with the data the sidebands of the signal region. I want to show you here just I mean, an example of the kind of agreement we have of data with Monte Carlo with for this variable that actually is the difference of energy expected for the decay short measured on the 6 gamma samples normalized to the standard deviation. And you see the several components coming from, because the background here, the difficult background to reject is the background coming from the 2 by 0 signal. We added 2 accidental clusters coming from background, from machine background, or even the splitting. I mean, when you reconstruct instead of 1, 2 clusters. So these are particular categories of events that we have. We are studying, but we are confident we have under control. So the expected sensitivity for the measurement of the branching ratio is below 10 to the minus 8. This is the status. Obviously, I cannot show the result today. So another result that we obtained some time ago concerning the K-short physics is the semi-leptonic charge asymmetry. This asymmetry is related to CP violation. If found different from 0, you can construct an asymmetry for the K-long. Let me say, quoted marks, easier to measure, and for the K-short. Easier, I mean, not easier. Okay, you need the pure K-short source, and actually, as I showed you, the Chloe, the entangled neutral kanon system in Chloe is actually the good source of K-short. Okay, so we already measured this asymmetry with the subsample of data with this precision of 1%, but we recently improved the precision, enlarging the data sample analyzed. The technique, I mean, to identify this kind of decays by nu is similar to what I have shown for the muon. Here you have at the end of the analysis, you see these. This is a logarithmic scale, the peak very well visible, I mean, under the, and these are other backgrounds, but the peak of the signal is here for here is for the E minus and here for the E plus. And when you combine this result to get the asymmetry, this is the result of the asymmetry that you obtain with an uncertainty that is reduced by half. Then you combine with the old result, you see here in this plot, the old result, the new one, the combination, that are still consistent with the CPT invariants and the value that has been found in the K-long with much higher precision by KTEV. From so this information from the combination of the asymmetries and having as input these quantities from other experiments, you can extract, I mean, new evaluations, I mean, more precise evaluation of these parameters that are CPT violating parameter in the decay, semi-leptonic decay, X minus and Y with the precision at the level 10 to the minus 3. And we are thinking to also improve still improving, I mean, this result with the analysis of the full data set. Concerning entangled kaons, okay, the studies, this is the situation, I mean, these are...
Again, you have 10 minutes.
Yes, thank you. So concerning entangled, the analysis of the pair, okay, of the two counts, the two decays. So recently we analyzed okay, this channel that is a kind of benchmark for Chloe for testing, I mean, for searching for the decoherence effect and CPT violation. The two decays, the two kaons that decay at the same time, the decay in the same final state by plus, by minus, by plus, by minus. So with this channel that is CP violating channel, you can test the coherence of the entangled state. Just for instance, in a naive model, when you put, you use a naive decoherence parameter multiplying the interference term, 1 minus, okay, and so the quantum mechanics simply predicts zeta equals 0 and zeta equal 1 is just the full decoherence, I mean, in the system. Hey, you can see here the expected distribution of these kind of events as a function of the difference of time of the two decays, where the quantum mechanics, as I said, predicts 0 for the decoherence parameter and total destructive interference at 0 different of times. And obviously, if you have decoherence, you start filling this hole. So this, so you can test with this channel this naive model, but this model can be made more specific in the case of, I mean, quantum gravity inspired phenomenological models. For instance, here in this case, formally you use the density matrix formalism, and you have, for instance, 3 parameters, alpha, beta, and gamma, that are CPT violating and inducing the coherence. In the simplest scenario, and with complete positivity, they end up with they are, I mean, you have only one independent parameter, gamma, that in this scenario cannot be, I mean, you should be at most of the order of nk square over m Planck. That means 10 to the minus 20 GeV. And again, in this scenario, you can also have an effect that is called the omega effect, in which the purity, I mean, of the initial state, I mean, the totally the anti-symmetry of the initial state is broken by CPT violation, and you add the small symmetric part. So these models have been tested already in Chloe, and the results have been shown several times. You have here the measurement, okay, with the precision, especially gamma, you see at the level 3, 10 to the minus 21 GeV, has been already measured and published by Chloe, all these models. Now we improved this analysis, enlarging the data set sample. Now we are analyzing 1.7 inverse femtobarn, and improved, for instance, the resolution in the delta T variable. That was a crucial variable to improve the precision of this result, and improved the evaluation of the non-resonant background that was affecting just the first bins in the delta T distribution. So we made a much more refined evaluation of this background, looking, for instance, okay, and this two-dimensional plot. You see here the signal, the peak of the signal, and the flat background distributed along the second diagonal. So after taking into account all these effects, obviously the delta T's resolution, the uncertainty and the knowledge of the delta T's resolution, efficiency, regeneration on the beam pipe wall, etc., we end up, okay, and here you see the distribution with these, okay, the points are the data, and the histogram are the result of the fit with all the components. And the results of the parameters, okay, making the fit on this distribution with several models, we end up with these new results that are improved by more than a factor 2 with respect to before. You see, gamma is now from the statistical uncertainty. The results were dominated by the statistics. The statistical uncertainty on gamma is 0.9 10 to the minus 21 GV, for instance. From the module of omega, we are also able to, okay, from this, okay, the parameters that are constrained to be positive are constrained, okay, with a simple procedure, and also we can put an upper limit to the hypothetical branch ratio of phi in k-short 2.4 10 to the minus 7 at 90% confidence level. So this was one result. Another result that an analysis that is going on that is the one that tests in a, let's say, direct way the symmetries T and CPT. This is based on the fact that we can exploit the entanglement to prepare the initial state. For instance, okay, if you want to, okay, study the transition K0 in K minus, K plus and K minus here are, let's say, the CP eigenstates, not to be confused with the charge counts. So if you observe a K0 decay on one side, you prepare on the opposite side a K0 orthogonal due to the entanglement, and then you can observe the transition K0 and K minus. Now, to make a test of CPT, for instance, you need to observe the CPT conjugated transition. There is no way to prepare an initial K minus decay no known but the exploitation of the entanglement, and means observing a K plus on the opposite side, and so preparing at the initial state a K minus on the opposite side. So based on the study of these transitions, you can do several combinations of the all possible transitions and construct this ratio of probabilities for T, CPT, but also for CP. And these ratios are constrained to be one unity in case of CP, of the symmetry invariance. So a deviation from one is a clear evidence of breaking of the symmetry. So we studied in CHLOE all the possible combination of final states in the entangled pairs decaying in these two final states, for instance, semileptonic 3 by 0 or pi plus pi minus semileptonic. Is a very complicated analysis because implies the study and the comparison of these final states with all possible combination of the final state. It's very complicated analysis. Okay, you construct with what you observed experimentally, I mean, the ratios proportional to, but okay, the ratios, let's say, as a function of the difference of time, the ratio that I shown before to test the symmetries. And I'm very proud to show this slide is just a very, I mean, let's say, preliminary result. The analysis is almost completed. All the systematics effects have been thoroughly studied. However, I cannot show today, but what I can show you is, okay, these results for all the ratios and also the double ratios that are more robust observables, let's say, from an experimental point of view. The T observables compared with what you expect from CP violation observed, the observed CP violation and assuming CPT invariance, the ratios and double ratio CPT observables compared with CPT invariance that in this case is 1, and also as a benchmark, let's say, the CP observables, okay, and with what you expect from the known CP violation that, okay, from the PDG. Here are some examples of this ratio as a function of delta T. Look that this ratio actually is measured with okay, higher precision than with respect to the others, but it's still consistent with what you expect. So to conclude, so the entangled neutral count system at Daphne, at the FI Factory, is really, to me, a unique laboratory for studying K-short physics, to study discrete symmetries, to test quantum mechanics in the most, I mean, the superposition principle, essentially, and so to search for the coherence effects that could be connected with the, I mean, a quantum gravity extension, let's say, of the theory. So the CHLOE 2 experiment at upgraded Daphne completed the data taking, and overall CHLOE and CHLOE 2 provided, I mean, a huge sample of data, which is unique for typology and statistical significance, and we are still analyzing it. So today, what I've shown concerning K-short, I've shown the first measurement of the KS mu3 branching ratio, the status of the search for K-short 3.0, and the measurement of the K-short, the improved measurement of the K-short symplectonic asymmetries. Concerning studies, I mean, on the entanglement search of the coherence, there are new results with the channel CP violating channel K-short K-long in the pi plus, pi minus, and is almost completed. I have shown the status of the analysis of the first direct test of TNCPT neutral count transitions. Obviously, there are several other analyses that are going on. And okay, so for the complete list, you can have a look to the physics program of CHLOE 2 that is in these references. So let me conclude that, however, the analysis of the CHLOE data is not the end of the CHLOE detector. Okay, CHLOE has a future, let me say, as a bright future, because the CHLOE detector, in particular the magnet and the electromagnetic calorimeter, that is very, as I told you, has a performance in terms of resolution, timing resolution, and energy resolution, very, very, very good, will be reused, will be disinstalled by Frascati, from Frascati, and will be installed in the Dune experiment for the search. Okay, OCP violation in neutrino sector is a long baseline experiment at Fermilab, and you will see this detector, I mean the CHLOE detector, the calorimeter and the magnet appearing in the short, in the near detector of Dune. The name will be no more CHLOE but SEND. Obviously, the tracker will be changed for performing for the next, I think, in the long, I mean, it's a long-term experiment with an horizon of, I would say, 10, 20 years. And so CHLOE will continue to be on operation, at least a part of the detector, for this experiment. Okay, thank you very much.
Thank you very much. Are there any questions or comments? Not in the room, online? So there are no questions, so let's thank Antonio.
Sorry, I have one question about this very last part of this Dune. So what is this lifetime of this detector? So do you use the original calorimeter for next 20 years?
Sorry? The calorimeter, I mean, is yes, because absolutely yes, because the calorimeter is okay, made of lead scintillating fibers, has optimal performance already in Chloe, and has been proved to be suitable, but more than suitable, optimal for the near detector of Dune. I mean, with the where the neutrino beam, I remind you, is 1 to GeV, of the order of few GeV, obviously, after a renovation of the electronics for sure will be, replaced. Is no more. This is obvious, but what is important is that the calorimeter, the LED and the scintillating fibers, the readout, the photomultipliers able to work in the magnetic field of Chloe, the coil, and the iron yoke of Chloe will be reused, and actually the value of this equipment, if you are going to build from scratch, is of the order of $100 million. So is not negligible. So and actually, this is an in-kind contribution of INFN and Italy for the Dune experiment.
I see. Thank you.
Okay.
So thank you very much. Let's thank Antonio Di Domenico again.
Thank you.
I don't know if yeah.
Hello.
Online. Okay. Hola, Rui. So, this is me. The next talk will be by Rui Santos on CP violation measurements at the LHC.
Okay, let me see. Can you see everything? No, wait.
Yeah.
Okay, now I think it's ready. Okay, so first of all, thanks the organizer for the invitation. I was supposed to be there. I even bought my flights, but British Airways kept changing my flight, and so at some point I had to give up, which is a pity, because I will not be on the excursion, which is really the worst part of it all. Anyway, I'm going to talk about CP violation measurements, not at the LHC. What I will use some very simple models to try to motivate or not the searches for direct CP violation at the LHC and future colliders. So most of the things that I will say are related to this benchmark model that we have been using for a while, which is the simplest version of the complex 2x doublet model, which we call C2HDM. I divided this into seasons. So the season 1 is before the first measurements of the LHC on the CP violation of the Yukawas. There is, I will discuss the large CP components of the Yukawa couplings and show you how this relates to what has been measured so far in HTT and H-tau tau. And then there is this combination of 3 decays, which is also a sign, could be a sign of CP violation, although these are 3-level decays. But if you don't see the particles, you don't have a way to combine these decays, but you can combine them inside the loop, and this is something that I will tell you in the end. Okay, so very quickly, the C2HDM. So you have here the potential. I think by now everybody has seen this potential at least 100 times. This is, we have now this M12 squared and lambda 5 to be complex, which means that you can have CP violation. We have decided to use a parameterization that is closely related to the 2HDM. So still 10 beta is the ratio of the vacuum expectation values. You still have 2 charge Higgs. it is just that instead of what you have in the CP conserving case, which are 2 CP even and 1 CP odd, you just have 3 scalars. And also because you have now a mixing matrix between these 3 scalars, instead of just 1 rotation angle, you have 3 rotation angles. So instead of alpha, you have alpha 1, alpha 2, and alpha 3. So these are the main differences between the 2HDM and the complex 2HDM. We use as independent parameters tan beta, the rotation angles, and the masses, except one of the masses, but this is not important for what I will be saying next. Okay, so what are the differences in the couplings if you look at the couplings of the standard model and then you go to the 2HDM and then to the complex 2HDM? So the difference to the 2HDM, if you consider the lightest of this CP even Higgs in the case of the 2HDM, is just that you multiply the coupling of the standard model by sine beta minus alpha. And if you go to the complex 2HDM, then you have the coupling of the 2HDM multiplied by cosine alpha 2. So this alpha 2, of course, is related to CP violation. And if you have sine alpha 2 equal to 0, then H is a pure scalar. And if you have it equal to 1, then it is a pure pseudoscalar. So this is the pseudoscalar component of the doublet. Now, if you look at this is an effective Lagrangian, but if you look at the C2HDM, you have exactly the same structure that you have in the standard model and in the 2HDM at tree level. So there is absolutely no difference. The only difference is that you have to multiply the coupling of the standard model by cosine alpha 2 and by sine beta minus alpha. This alpha here is in fact alpha 1, but it's not important also. So the other couplings only appear at the one loop level. So the big difference is in the couplings, in the Yukawa couplings, because we decided. Well, I will not discuss here that we have a lot of different types and why. Well, I will show you the coupling for the types, but we have a Z2 symmetry, which means that we have no flavor changing neutral currents. And the difference here is that we have this product of angles divided by sine beta, and again, a product of angles divided by tan beta. And we have a coupling that is proportional to gamma phi. So we have the CP even and the CP odd coupling. And so this means that we have a CP violating model. Because we fixed for all types the up quarks, then this means that this is the same for all types, and this is important for what I will show you next. In particular for type 2, you have a difference here, and the difference is that instead of having sine beta, you have cosine beta, and instead of having 1 over tan beta, you have this coupling multiplied by tan beta. And this is important because tan beta is constrained to be above more or less 1, and it's not very constrained. You can have it order 10, and this means that even if R13 is small, this component can be large, while for the top, it has to be small. Okay, so these are the different types. Type 1, where you have the same couplings for all fermions. Then you have type 2, where you have this difference. For the up quarks, you have cosine alpha over sine beta, and for the others, you have minus sine alpha over cosine beta. And then you have the other two, which in principle are not that important, but for what I will tell you next, they are important because of the constraints of the EDM that act very differently on the different models. Now, this is for the 2HDM. For the C2HDM, again, you have the same cosine alpha 2 that you had for the coupling to gauge bosons, and the coupling is the same. This part here is the same for the 2HDM. And then you have either sine alpha multiplied by tan beta or sine alpha divided by tan beta. So again, here, this means that this component, even if sine alpha of alpha 2 is of course below 1, if tan beta can be large, this means that this component can be large, except for the case when it is divided by tan beta. So the first thing, of course, you think of doing is to understand what are the bounds on the Yukawa couplings from rates only. And if you do this, you realize, and if you take tan beta to be above 1, you realize that these are the bounds that you have for alpha 2. And here you see the bounds here below. You see the bounds that you have in the type 2 model for the coupling. So these are really the couplings. And you see that for the top, you can only have this part here after you include the EDMs. Here, these are the couplings to the B's and to the taus, which I remind you are exactly the same in type 2. And this means that if you don't take the EDMs, you can have all these possibilities. But if you then take the EDMs, you just have this dark green part here that is still allowed. Okay, so what happens then is that if you start using the constraints from the EDMs for the models, you realize that they act very differently on different models. And although in some models they are killed, and so you cannot have these regions here. In some other models you can have them, and this leads to this kind of possibility, which is the following. You can have a scalar, we call it here H2, and H2 can look exactly like a CP even scalar if you're looking at PP to HTT bar, because it's right here on this region, and this is 1, meaning the CPO component is 0. And at the same time, you can see what happens for the taus. And for the taus, you can have here points that are completely CP odd. The CP even term is 0. And so this means that one strange way of looking at CP violation is to have the same particle in one channel behaving like a CP even component and behaving like a CP even scalar, and in the other channel behaving like a CP odd scalar. And we just redid the scan with the new EDM results, and we found exactly the same. So still, this is a possibility. Okay. Now, then we just looked at future colliders to see what happens, and of course things will get, the constraints will get bigger and bigger to the point where things are really in a very narrow region. But of course, when you reach this level, you have to start worrying about radiative corrections. So the results that I present here for click are just results still without radiative corrections, and we see that these components become very, very small. And in particular, if you look at the angle alpha 2, you will see that most of it will, these are for 3 different scenarios, the 3 different colors. The red one is the last run, and you see here that the angle in degrees is below -3 and 3 degrees. And this means that then this is the red part here, which means that even if we don't look at direct CP violation, at some point we will have very strong constraints on the couplings to tops and Bs, even if that will just happen at future colliders. So one thing that we did a long time ago is this combination of 3 decays. Well, there are many combinations of 3 decays that you can use, but if you assume that one of the particles has a definite CP, then you will come into a contradiction looking at the other possible decays. Now, of course, this is all very interesting, but you need to find particles to test this, and because you haven't found anything yet, there is no way to test this unless you test them inside the loop, and this is what I will discuss at the end. Okay, so finally, very recently, the Atlas and CMS have started to probe directly the CP-odd couplings of the Higgs, of the 125 Higgs, in HTT and H-tau-tau. And so these are the results for HTT. You see here that for HTT, it is not that important because as you saw before, the results from the rates are already very constraining, and so there is nothing really new here except that it is very good to have direct results. And so the conclusion here is that all measurements are consistent with the standard model, and the possibility of a CP-odd coupling is constrained. A pure CP-odd coupling is excluded at 3.9 sigma, and alpha for above 46 degrees is excluded at 95% confidence level. This is not still competitive with what you get from rates, but I think that probably it will in the future. Okay, so the other measurement is from CMS, is in the H-tau-tau channel, and you see here that these are the results: 68%, 95, and 99.7. So if you look at this band here, you'll see that this scenario where you consider that one DH is a pure CP-even scalar in H-tau-tau and a pure CP-odd in HTT, sorry, and a pure CP-odd in A to tau-tau is excluded now. So this plot excludes this possibility, and so this is something new that was not there before. So everything that can be done for the tau-tau and for the BB, I expect that the others will take much longer, but at least you have the tau-tau and the BB. I expect will tell us something about the possibilities in the different models. One thing that we're trying to do at the moment, because
we have now 10 minutes.
Okay. One thing that this was H2 gamma gamma, and one thing that we are trying to do at the moment is the decays to BB, and we have used several variables present in the literature, and we have included new ones, and these are very preliminary plots. We have included all the asymmetries that we could find, and so far what we saw, if you look at the results that we have now, is that these are almost competitive to what was done so far by Atlas, but we are still not there yet. But it would be interesting to have a result also from the BB bar side. This same idea, you could think that you could use it for BBH instead of TTH, but the problem is that this interference term when you look at this process, here, this can be divided in two terms: one that is proportional to A squared plus B squared, and one that is proportional to A squared minus B squared in this notation. But the problem is that the term that is proportional to A squared minus B squared is proportional to the Fermion mass. So if it is a top, it's fine. If it is a bottom, you cannot do it. So we showed here that it is not possible to find anything for the B. Very recently, there was a paper also based on rates where they claim that there is a possibility of looking at BBH in the high luminosity LHC and also in the FCCHH. Okay, then you can also prepare searches if you find a lighter Higgs, and this is just to show what is the relation between the luminosity and the couplings. And then you can put all this together and just see what happens. And this is a plot for the H125 in the C2HDM. And this is the constraints that we have so far, these black bars here. And the points, the H125 points are here in this region. So this is something that can be used to constrain also the C2HDM. Sorry. So let's move to the couplings to gauge bosons, which is something harder. You have all these different ways of presenting the effective couplings in the Lagrangian or in the Lagrangian or in the amplitude or in the vertex. But the only important point here is the following. These are the terms that are identical to the standard model, and they are also the only term in the C2HDM and in the standard model at tree level. And then you have the terms that come from a CP violating operator. And so what you want to know is what are the results and what can you expect for the future. And the results now from CMS and Atlas are that this H3 over A1 is between minus 0.81 and 0.31. And these are this was done, the latest results are from 2019. They are based on, again, on angular distributions. And now you can ask if it is worth to keep this search at the LHC and even at future colliders. And as you know, if you want to see CP violation in this vertex in the standard model, you have to go to 3 loop. And if you do an estimate, you reach the value of 10 to the minus 23. So of course here there is no way you can find anything. But if you go to the C2HDM and you do the same calculation, and at the same time you use the values that we have so far for the constraints, you reach a value that is of the order of 6.6 times 10 to the minus 4, which let us say that it's of the order of 10 to the minus 3. And this tells you from the theoretical side what the experiments are up against. So 10 to the minus 3 should be seen as a benchmark number that you should reach. Now, very recently, we started with Atlas. We started to probe this effective vertex in WWH with W decaying to lepton U and H to BB bar. We have some preliminary results. The preliminary results are not even close to 10 to the minus 3. So I decided to see what we can expect for the future. And there is an estimate for 3000 inverse femtobarn from CMS. And this gives you a number of the order of 10 to the minus 2. And even if you go to the ILC, and this is from Ogawa PhD thesis from 2018, you will see that they conclude that the most comprehensive study for future colliders so far was performed for the ILC, and these are results for this polarized beam to center of mass energy is 250 with 250 inverse femtobarn and 500 with 500 inverse femtobarn, and the limits were close 10 to the minus 1, 10 to the minus 2, 10 to the minus 2 again for the W, and 10 to the minus 3 for the Z. So it's not easy, but it's not impossible at the same time. Okay, sorry. Okay, so let me finish with the dark sector and CP violation. These are results from the past, that were used in this paper for the C2HDM. And then here, these two papers. So first, the first paper proposed a CP violating dark sector. And then we tried to understand what we could do with the 3D case that I showed you before to see what we could see at the LHC as well. So in particular, our model is just a model where we have two doublets and one singlet. And this extra term provides CP violation if A is complex. And I will not discuss this because it's not important, but I will discuss this. So what you see here, if you look at this coupling, maybe wait, let me show you this one. So if you look at the triple Z coupling, you will see that this combination of 3D cases that would show you CP violation are also the combination that is inside this loop. So you have H1, H2, and the H3, H2 on this side, and H1, H3 here. And so you can also look indirectly at this combination of 3D cases to look for CP violation. And let me just go up. And you see here that this term F4 that measures CP violation is close to 10 to the minus 5, and so the typical maximum values for F4 are below 10 to the minus 4, and this is not only for the case of the dark sector, but also the case for the C2HDM that was discussed in this paper here. And these are, again, our results for F4, the 10 times 10 to the minus 5. So you see here again that these are the results that we have. And what was measured by CMS and Atlas at the moment are values close to 10 to the minus 3. So we're still a bit far away, but maybe we can get there. Okay, so let me conclude. So regarding SIGs and fermions, there are these two ongoing direct measurements of Yukawa couplings with top quarks. If you look at the production side, and with tau leptons, if you look at the decays, and at the time, the other Yukawas are measured indirectly by the rates. And of course, CDMs play a major role here, as they will do even more in the future. Regarding Higgs and gauge couplings, the CP violating terms appear at two-loop level, but there are extensions, CP violating extensions, where one loop already gives you a number, but the coefficients, at least for the C2HDM, are small, but maybe they are reachable. So regarding the invisible Higgs, if there is some invisible CP violation around, maybe it can be measured indirectly, like in anomalous triple gauge boson couplings, and which I hope at least that the end of season 2 will come with stunning revelations. Thank you.
Thank you very much. Any questions? Yes, there is one question by Tanya.
About 5 minutes for the talk. I have 2 questions, in fact.
It's very hard to understand what you're saying, Tanya.
Okay, just 1 second. Is it better?
Slightly. Okay, I think I will understand now. Go ahead.
Okay, so I have 2 questions. The first one is for slide 10. Maybe you can go.
You said 10? You said slide 10?
Yeah, exactly. So I was a bit confused. I mean, are these 2 different particles, and you explicitly
No, this is the same particle.
They are mass degenerate, and then one is
No. It is the same particle.
Or is it one particle with different couplings?
It is the same. You cannot hear me, it seems. It is the same particle.
Okay, so it just behaves as if it was, okay.
Yeah, that's why it is a strange case of CP violation, a very strange case of CP violation. because it is exactly the same. I mean, this tells you that you really have to probe each of the couplings, because you can have something that you can have the same particle behaving differently in different couplings.
Okay, is this, oops, is this very fine-tuned, or is it typical?
No, it's zero fine-tuned. Well, come on, it's zero fine-tuned from the theoretical point of view. It is fine-tuned in the sense that you have a parameter space and you have to go to a particular place, right?
Yeah, okay. Oops. What is happening? I had another question.
I mean, if the
question was for this model with CP violation and dark matter, maybe the first slide.
On the what? Sorry.
CP violation and dark matter, the last topic.
Yeah.
I'm just wondering, do you have one dark matter candidate or several here? Because you say if the three scalars are invisible, are they all contributing to dark matter, or you only have one, the lightest one?
No, only the lightest one, of course.
Sorry, can you repeat it? I couldn't hear it.
Can you what?
Can you repeat your answer, please?
Yes, one of them will be the lightest, yes.
Okay, thank you.
So there's another question.
Thanks for the talk. So, I mean, I saw that in one of your previous slides, you had this interaction H-Z dual, right? Z mu nu.
Yeah.
So the H is what? Is a CP odd X scalar, or what is it?
It's a CP indefinite scalar.
Interaction comes from related to some kind of anomaly.
Yeah.
It's you are not. I mean, is a scalar or pseudo-scalar component at H?
It's a CP indefinite scalar.
Okay, all right. Okay, but that comes. I mean, how does it appear? This contribution is included at tree level, or?
No, it's not included at tree level. I mean, in the C2 HDM, as I told, the coupling to gauge bosons is exactly the same as the one in the standard model.
All right. Thank you.
Okay, so thank you very much, and I think we finish here because there are no more questions. And thank you for your talk.
No, there are questions.
Bogdan has raised his hand.
Online, there was not.
Yes, I had a question. Hello, Rui.
Hello.
Nice talk. I have a simple question. I mean, in Z2 symmetric model, in the alignment limit, CP is vanishing.
Yeah.
So I wonder if you see that numerically imposing the constraint from Higgs vector coupling.
Exactly, you're right. If I align, everything is killed. I mean, even the loop, you can see that.
No, yeah, everything should be killed.
Yeah.
Okay, very
right.
good. Thank you.
So thank you again, and let's thank the speaker again. So bye.